My talk is on hydrogen, but my name is Jaisen Mody, and I am a retired consultant. I retired from Portland General Electric after 42 years, and prior to that, I was with Bechtel. Most of my career has been in power generation. So I've been researching hydrogen lately, and so this is the hydrogen 101 type. For people that know hydrogen, this may be boring, but I'll start off with some basic 101 on hydrogen. It's the most abundant element in the universe. It can exist in gas or as liquid. It's very light, 93% lighter than air, rapidly dissipates. And it's 88% lighter than methane, which is your natural gas. Non-toxic, no CO2 emissions. And the hydrogen flame is 10% of the radiant heat of a hydrocarbon fire. It's less volatile, and the explosive power is 22 times less than gasoline vapor. And so the challenge is it's odorless. It'll require an odorant and other safety measures. It leaks very easily. Very low ignition energy. It's the most flammable element on Earth. And it's difficult to transport. It's very dense by weight, but not by volume. So it has to be compressed or liquefied for transportation or storage. And then you have the losses with hydrogen production, compression, liquefaction, and transportation. So, there's a competition between the hydrogen molecule and the lithium electron for transportation. I mean, everyone's looking at electric cars and then hydrogen cars, and hydrogen transportation is coming. So I compared the molecules and the electrons. The hydrogen molecule has got low efficiency. It's fast charging, high energy per mass. And then your lithium electron has got higher efficiency, and there is an existing distribution structure, but it's slow charging and low energy per mass. In my opinion, both of these will coexist. You'll have electric cars in the future, but maybe for long haul transportation and other vehicles, you'll probably go to hydrogen fuel cells. So everyone wants to have green hydrogen. That's the most common form of hydrogen that people are wanting to have these days. So green hydrogen is when hydrogen is produced with renewable energy, and it's near zero carbon emissions. So carbon emissions are defined by DOE, and it's 0.45 kg CO2 per kg of hydrogen. That's considered green. So you make it from green energy. Let's see if I can get this pointer going. Green energy, electrolysis, and then green hydrogen. It's very simple. Then you have blue hydrogen. Blue hydrogen is made from gas, natural gas, steam method reformation. It's a chemical process. You have some CO2, and that CO2 gets captured. So there's CO2. First, you have to strip the CO2 out, and then you have to capture it in geological formations or sell it to some people. So there's an industrial demand for CO2, and that produces blue hydrogen. Another shade of hydrogen is gray hydrogen, and this is where same process, SMR, but you don't capture the hydrogen, so it's called gray hydrogen. Everything else is the same as blue. Then comes black or brown hydrogen. This is from coal gasification. So you take a lump of coal, you gasify it, and you get black hydrogen. And there's brown and black depending on the coal you use. White hydrogen. This is the natural occurring in geological formations, very deep down in the earth. It's very hard to extract, and it's not economical, but it exists. So this is getting a lot of attention these days. Is the pink hydrogen. This is made from nuclear power. Nuclear power does not generate any CO2. So nuclear power plants, especially the new ones that are coming online, have a high temperature at the back end. So that's just the right process that you need for making hydrogen. So you're pairing nuclear power with the solid oxide electrolyzers, which is a good marriage because the solid oxide electrolyzers like high temperatures at the back end. So I think this could be very prominent in the future. Then we have the turquoise hydrogen. This is created by taking natural gas, and it's called methane pyrolysis, where you don't produce any CO2, but you produce carbon. So that carbon can be used for carbon fiber, or it can be disposed of much easier than CO2. So how do you produce hydrogen? Green and pink are used, by splitting water. You have the alkaline technology, which is mature, uses potassium hydroxide. It's the only mature technology right now that's bankable for larger installations. And here comes PEM at the background. It's fastly catching up for smaller plants, faster response time, and then you have the solid oxide, which is still in experimental stage, I think. Blue hydrogen is again SMR, and there's a new process called autothermal refining of methane, which is the ATR process. It's also a chemical process. And then turquoise hydrogen is methane pyrolysis. So how do you site a hydrogen production plant for green hydrogen, which is what you want to do? So you have to look at, how to site this close to a grid where there is a lot of renewable energy, high availability of wind or solar, and then the plans for grid expansion in that area. And you have to have a hydrogen off-takers nearby. And this is the new one. This is the tax consideration from the Treasury, the 45V and 45Y, the three pillars. It gets very complicated because now there's a problem with hydro and nuclear because those plants have to be new for producing hydrogen. There is a lot of pushback on that's going on with the Treasury. So I don't know what the final result will be, but it seems like to get the tax benefit, it's a run. It's a marathon. So the hydrogen uses, I think you all know this, but power systems. This is where I work. You can use it for power generation, islanding grid, long-term storage, backup generation, chemicals, fertilizers, methanol, steel, semiconductors, aviation and ocean, ferries, shipping, light and long-haul aviations, drones. The military likes the hydrogen in the fuel cell because it's got a higher payload, can go longer distances. Then in transportation, buses, trains, and this is where I think the real benefit is long-haul trucks that can go 500 miles without charging and don't decay in colder weather. And then these are the two toots in foreign countries. There's a lot of benefits of decarbonizing these two toots with hydrogen. So real benefits is the immediate greenhouse gas emission reductions. It can replace fossil hydrogen wherever it's currently used. It's just a drop-in. Supports grid reliability, and it's a solution for hard to abate sectors. And it's long-term storage. People don't realize, but long-term storage right now is batteries. You get 8 hours, maybe 16 hours, maybe longer batteries, but it's like 2 days, 3 days. Hydrogen can do seasonal storage as long as you can store it. And so storage is a problem, but hydrogen provides long-term storage. I'm having trouble seeing this. So what are the challenges? So I put this in buckets here. Lack of infrastructure. Hydrogen doesn't have all the charging stations like the electric cars do. It's a chicken and the egg problem. Both production and use should develop together, but they're kind of far apart right now. Safety. A lot of misconception and fear of explosions. Water. I think everyone knows that electrolysis requires water. About 1/4 water is required to produce 1 kg of hydrogen. And that's not the only water consumption. You need a lot of water to cool the electronics that go with the electrolyzer, and that's pretty significant. And then leakage. It's a very lightweight molecule, so it has to be carefully monitored for leakage. I'll go through this quickly. This is drop-in fuel for turbines. There are turbines right now that can do 30% hydrogen and going to 100%. And there are some issues with NOx. And you have to modify the combustors and the delivery systems. But this is happening right now. We have gas turbines that can run on hydrogen, and the future is at some point to replace the natural gas with hydrogen for these peaker plants. Chemical and processing, we talked about that. Fertilizer is the big deal here, and also the methanol and ammonia. All of this can be used and can decarbonize by using green hydrogen. Fertilizer is a focus in the US right now. There's a lot of demand for green fertilizer in Europe and outside the US. And we have a lot of places in the US where we can have fertilizer plants close to hydrogen production and produce green fertilizer. So we talked about long haul trucking being very useful. A good candidate for hydrogen, and the tools, forklifts. So right now, there's a lot of forklifts in the Amazon data centers that are using fuel cells and a hydrogen cylinder. So they're decarbonizing the data centers by using these forklifts that don't use diesel. Storing is difficult. It's a very light molecule. It has to be compressed, but salt caverns, and this is a we don't have salt caverns everywhere, but this is the best way to store hydrogen. You can store gigawatts worth of power in salt caverns, and you can keep making new salt caverns where there's salt formations. They're doing this in Utah right now. There's a project called ACES that's happening today, where they'll store hydrogen in salt caverns and run a very large gas turbine. We are also focusing on stacking in pipelines. There's 3 million miles of existing gas pipelines in US, and you could blend hydrogen with natural gas and store it that way. So the pipeline considerations is pretty significant. For purity pipelines, which is 100% pipelines, you need higher strength pipes. You have to do higher pressure, and you probably have to use new microalloy or line pipes. And there's a lot of ongoing research going on today on materials that will bring down cost of hydrogen pipelines. So let's talk about embrittlement. We all know that introducing the hydrogen molecule in a carbon steel pipeline causes an embrittlement. And so embrittlement is a material will fracture without appreciable prior plastic deformation. Typical brittle materials are glass, concrete, ceramic, stone gray, cast iron. And what is hydrogen embrittlement? We need stress and the diffusion of the hydrogen molecule to start the embrittlement process. So there's a lot of research on embrittlement and new pipelines, ASME codes that have been published, especially the API 5L for carbon steel, for microalloyed high pressure hydrogen gas pipeline service. Older pipelines that are 40 years old have to be evaluated for percentage of hydrogen blending. Europeans are blending at higher rates. The US is considering 5 to 10% right now, and in Europe they're doing 30 to 40%. The problem on new pipelines is easy to solve. The problem on older pipelines where you're thinking of blending is a little more difficult. So, the conclusion is that hydrogen has the potential of 100% decarbonizing certain segments of our economy. The zero carbon roadmap requires regional developments and execution strategy. We talked about steel and how to decarbonize sectors that can achieve immediate benefit by replacing fossil hydrogen with green hydrogen. So what's jump-starting this hydrogen economy is the Inflation Reduction Act, the IRA Act, which is pushing almost $8 billion into hydrogen hubs and giving all kinds of tax incentives. And we think that will start the production process for hydrogen. And when you start the production of hydrogen, the demand will come. We have a lot to learn to capture the true societal benefits of hydrogen. And for renewable hydrogen to deliver its promise, these challenges must be addressed now. It's easier to build it right the first time and fix it later. A lot of excitement on hydrogen these days because of this IRA Act that just went through, as I was telling you about. These hydrogen hubs, 8 of them are being developed right now, and they all will be coming online in the 2032, 2035 timeframe. And I think there's a lot of production that will happen when all these hubs are online. And that's my speech on Hydrogen 101. Questions? You have a question.
So how much percentage of hydrogen can be mixed together with gas turbine without retrofitting?
So right now you can do 10% is easy, no problem, same combustor. 30% you require a little modification. You require a pre-mixed combustor, which is very easy. But to go for over 30%, you have to change the combustor.
Okay, got it.
Yeah. So 30% to 100% you need a new combustor. And they are being developed by Mitsubishi, Siemens, and General Electric, all of them.
Okay, cool. One more question.
Sure.
So when you generate like hydrogen by like using the electrolyzer from water, what type of water can be used?
You need DI water, demineralized water.
Or mineralized
So you take water and then make it. You need a water plant.
Oh, okay.
Yeah. So there is expenses on. But there's a new electrolyzer that's coming on the market in the next 3 or 4 years, which will take salt water and make hydrogen.
Oh, really?
Yeah, no DI water.
Oh, that means like if there's
That'll be a game changer. Yeah.
yeah, if there's a ship
Yeah.
on the sea, they can like
That's
generate
right.
hydrogen themselves.
Yeah. I don't. Let's see if that happens. Yeah.
Oh, wow.
No, there are no stupid questions on
The only one
hydrogen.
that's going to see me after this is this guy. So I've been wondering this all day. I'm not that familiar with this, but what is the chemical equation for the hydrogen combustion?
What is the what?
Chemical equation for the hydrogen combustion? We always learn like there's like a hydrocarbon molecule like oxygen and then it gets CO2 water, right? That's what we learn in high school. But
Yeah.
what's it for
So oxyhydrogen is hydrogen and oxygen, and then you get steam basically. That's how you combust hydrogen. True combustion of hydrogen would be hydrogen in a boiler of some sort with oxygen, and you get steam and moisture. In a gas turbine, hydrogen is used the same way as natural gas. You compress it first, mix it with air, compress it, and you combust it, and then we get a lot more water moisture on the back end with hydrogen.
Okay, so that leads me to my second question. So you talked about the amount of water required to generate the hydrogen, and then a lot more water on the other end.
Electronics.
So what's the percentage that you could kind of consider it as a cycle? Like if you were
So for a 100 megawatt electrolyzer, you need about 300 GPM of water. Yeah. Which,
The whole cycle, you don't lose water in the cycle, basically.
yeah, you cool the water with a cooling tower and you bring it
yeah,
back.
so
You lose some water because of evaporation and all that, but you don't lose the water, but you need a lot of water, to circulate.
So just on that, so if you're using electrolysis to split water to make hydrogen, and you burn the hydrogen, do you lose that water molecule forever? Like if you think of a water cycle, normally it's a cycle, but if you split off the hydrogen and burn it, is it a consumption of water?
Yeah. So when you're splitting the water, you're making hydrogen and oxygen. That water, you're losing some water there. Yes. But you're not losing any water on the cooling side. You're losing some. You're just it's like a radiator.
What is the current cost of using hydrogen?
It's between $5 to $6 a kg, and with this Inflation Reduction Act, you can get a $3 per kg benefit. So it'll reduce it down to $2 to $3, which brings it in parity with natural gas. All right, guys. Thank you. I'm going to delete this thing, from my. I don't want to keep it here. Well, sir,
I need to run to the airport.
thank you very much.
I'll get you,
Yeah.
send you an email.
Yeah.
And I'll
Let's
see.
keep in touch. Yeah.
Absolutely. And
Yeah.
that's,
Yeah.
actually, at some point, I may need to go working with that. So, great to meet you. Yeah, great to meet you. Yeah, perfect. Well, yeah. At some
Yeah.
point, I will probably need to go have a customer that they're sitting in Vancouver.
Yeah.
So
Come visit me.
If I go, I'll call you for a visit.
I would love to, do something with you guys on a high level, like a board or
We
something.
need to send a picture. Let's take a picture. Let's send a picture to Pilar.
I'm trying to delete this thing.
Let's send a picture to Pilar.
Oh, a lot of,
We went through a lot together.
Yeah, I know. I'm glad I wasn't part of that. Anyway,